Okay, now that we've seen Sadie Carnot's derivation of the efficiency of a heat engine, let's take a look at what Clausius saw in those derivations and what led him to discover the entropy state function. So in the engine cycle, we found that the heat flow from the hot reservoir divided by the heat flow into the cold reservoir was equal to the negative of the ratio of the cold reservoir temperature to the hot reservoir temperature. Now, with just a little rearranging, that expression becomes this expression here, where now we have everything to do with the hot reservoir in the sense that the heat flow out of the hot reservoir divided by the temperature at which that heat flowed, plus the heat flow into the cold reservoir divided by the temperature which it flowed, adds together to give you 0. So the reversible heat flow divided by the temperature adds to 0 in one Carnot engine cycle. And this was a clue to Clausius that any state function, when you go through a cyclic process, will always have a change of 0. So here was a function that in one Carnot engine cycle was adding up to 0, this Q over temperature. So this has Clausius really intrigued, and he starts thinking carefully about this. And what he realized was that any reversible process can be broken up into a series of isothermal and adiabatic steps, with the heat only flowing during the isothermal processes. So here's an example, sort of how he was thinking on this. If I had a plot of pressure versus volume, and we're looking at a reversible process, so here with this solid green line moving from this state here to this state here, and in this plot I've drawn lines of isotherms and adiabats. So the dash, you can't see it very well, but there are dashed lines for the adiabats and solid lines for the isotherms. And so what you can do, and this is what Clausius realized, is that if I have my reversible process, which is this green line, I could connect my initial and final states by first moving along an adiabat, then along an isotherm, an adiabat, isotherm, continuing like this, and eventually I would end up at my final state, and that path would be a very, very rough approximation for the reversible path, which is a solid line in green. But you think, okay, that's not a very good approximation because it really deviates quite a bit. But the reason it deviates quite a bit is because I've drawn this grid of lines with some kind of gap between them, some coarse gap. But if I had drawn a finer grid, then you would see, like in this example here, between the same two states with the same process, I'm moving along a set of isotherms and adiabats that are much more closely following the process than in this case. And so just taking this idea, continuing to draw the grids finer and finer and finer, eventually your path of adiabats and isotherms is going to just completely be converged onto the actual reversible path. So clearly then, any reversible path can be broken up into these steps. And if you have a grid fine enough, you would not be able to, the approximation becomes exact. All right. So that means then for a reversible cyclic process, we expect then that the integral of dq, q is reversible heat flow, divided by the temperature is going to give you 0. And that is the behavior of a state function. And what Clausius realized is he had discovered a new state function in thermodynamics. And he called this state function entropy, and the differential change in the entropy is given here. So it's ds, S is the symbol he used for entropy, and for reversible processes, it's just a differential heat flow divided by the temperature at the boundary where that heat flows. Now, in the paper in 1865, Clausius decided that he was going to pick a Greek name because it was such an important quantity in science. And so he picked the Greek word that actually means transformation. But he intentionally, as he writes, I intentionally formed the word entropy so as to be as similar as possible to the word energy, so that both these quantities, which are to be known by these names, are so nearly related to each other in their physical significance that a certain similarity in their names seems to me advantageous. Okay, so he thought that this new state function is just as important as entropy in trying to understand thermodynamic, as entropy and energy were just as important, equally important in trying to understand thermodynamic processes. One thing I will note that if in his definition, instead of dividing by T, if Clausius had divided by RT, then that would have been, RT would have the dimensions of energy, Q has the dimensions of energy, and entropy would have been a dimensionless quantity. And that actually would have made it more consistent with what a more modern definition of what we now call information entropy. But that will be for some other class, not this class. So given Clausius's definition of the differential change in the entropy for a reversible process, we can look at some of the processes that we've looked at before where we've evaluated the heat that flowed. So first of all, any process where the entropy remains constant, we're going to call that process an isentropic process. So a new word to add to your vocabulary book for thermodynamics. So if we have a process where there's no heat flow, so any adiabatic process, any reversible adiabatic process, because we're still with insistence that we're using a reversible process here, any reversible adiabatic process, then we will have delta S of 0. So that means we have an isentropic process for a reversible adiabatic process. If you have a reversible isothermal process, well, then we integrate this expression up here, so from some initial to final state, but since it's isothermal, the temperature can slide out of the integral, and then we're just integrating the differential heat, and in a reversible process, then that would just give us this simple expression. So as an example, if you had the heat transfer in a reversible isothermal expansion of an ideal gas, we worked that out before to be given by this expression. So all we need to do is simply divide it by temperature, and that's the entropy change for the reversible isothermal expansion of an ideal gas. All right. Similarly, we looked at reversible phase transitions at constant pressure. Remember, we identified the delta H for the transition is the heat flow at constant pressure. So that means that that's the heat flow for that reversible process. We simply divide by the temperature at which that transition occurs, and that gives us the entropy change for the transition. So the entropy change for fusion is this, entropy change for sublimation is here, and the entropy change for vaporization here. The same equation, just changing the subscripts there. All right, and all of these three quantities are positive quantities. So that means that the entropy is increasing when you undergo fusion, say melting, sublimation, or vaporization. Another useful case is the entropy change when we're heating a sample, so we're increasing its temperature. So let's consider, first of all, we have the heating process done reversibly, so we know that the integral is dq over t, and then we'll consider the case of, say, heating a sample at constant pressure, which would be a more typical thing you would do in the lab. So for a reversible isobaric process, we would start out with this expression here, and since it's heating under constant pressure conditions, that would be the change in enthalpy during that reversible process. And of course, that enthalpy can be related to the heat capacity. So Cp times dt is equal to dH, if you remember from our definition of the constant pressure heat capacity. And then we can take this expression here and use a little calculus trick where dt over t actually becomes d ln of t, and then we get this expression here for the change in entropy for just reversible isobaric heating or cooling of the sample. So if you integrate it, the heat capacity on a scale that's a logarithmic scale of temperature between those two temperatures, then you'll get the change in the entropy that way. Okay. If the heat capacity here you can see is temperature dependent, which is generally true, but if you're in a small enough range where you're working where the system where the heat capacity is approximately constant, you could slide that out of that integral in that case, and then this integral becomes simple to evaluate, and you get this expression here. All right. Now, similarly, if you were doing heating under isochoric conditions, say constant volume conditions, you could have a very similar derivation here. So you should get an expression that looks just like this, and of course, under a very small range where the heat capacity can be approximated as constant, then you would get this expression here for the isochoric process. Now that we understand the quantitative measure of this new state function, entropy, what does it mean in terms of the thermodynamic system? Now, we'll learn more in the next chapter on statistical mechanics on what it means from a sort of microscopic point of view. But from the thermodynamic point of view, let's see what it tells us about our system and what we can and can't do with that system. So for example, imagine I'll do a plot. We know now we have a new state function. So let's plot the state of the system in terms of some point in the space of S versus U. So let's say I have a state at this point right here, state 1, and it undergoes some irreversible process where its entropy increases from state 1 to state 2. And we're going to do this irreversible process so that the energy remains identical. So this is a process where delta S increases while delta U stays constant. It's 0. So now what we're going to see is that a good example of this would be like the Joule expansion of an ideal gas into a vacuum. We saw this before where we took a gas that was on one side, we had a vacuum on the other. We opened the valve and we let it expand, and we had a situation where, because there was no work done, because it was expanding against the vacuum and it was surrounded by adiabatic walls, that delta U was equal to 0. But we do know that this was a spontaneous process, so we know that the entropy must increase. So this kind of plot would be a nice plot to sort of go along with this type of process here. Now, so we know in this case for an ideal gas, well, certainly we know that delta U is equal to 0, but for an ideal gas, we know that if delta U is equal to 0, then delta T is equal to 0 for an ideal gas. So we could then calculate the entropy change for going from this state to this state by finding a reversible process to connect these two states. So remember, the way we can determine the change in the state function for an irreversible process is find a reversible process that will connect the same two states. And in this case, we could connect those same two states by an isothermal expansion where heat and work are exchanging with the surroundings, but the net result is that in that process, delta T is 0 and delta U is 0, the same as this process for the final minus initial. So in that case, which we saw in the previous slide, we know the entropy change is given by this expression here. So this is just to show you one type of an example where we would have a situation where you would have an irreversible process where you would have the energy stay constant and you would increase in your entropy. But what we're interested now is to see how that entropy increase impacts the system's ability to do work. So what we're interested in is how is the work that I get from state 1 compare to the work that I get from state 2. So let's take a more deeper look at this. So let's imagine we have our system, a system that we're going to extract work out. So we're going to extract work by letting it expand as it's connected to some surroundings. So there's an isothermal process where it expands like this. Now, if I have my two states, what I'm going to do is I'm going to have a process where I let it expand and do work, and I'm going to bring state 1 to state 3, and then I'm going to compare that to taking state 2 to exactly the same state 3. So the change in the energy of state 1 and 2 going to state 3 is exactly the same, but they start from different initial entropies. So how does that affect the work that I'm able to get out of this system? So remember the first law, delta U is equal to Q plus W. So that means that for this system here, that the temperature of the surroundings where we're extracting the heat, this becomes, using Clausius definition, T delta S, okay? So remember our definition here, I'll just go back here, okay? So delta S is equal to Q over T. So in this case here, I can take for Q, T times delta S plus the work. That's my expression for the first law, which now includes Clausius' definition of entropy in it. So if I rearrange that, that tells me that the work that I extract out of the system is delta U minus T delta S, where T is the temperature of the surroundings where we're doing the heat exchange. All right. Now, the difference in the work from going from state 1 to 3 compared to state 2 to 3 is going to be here. So W13 minus W23. So I'm just going to do this, use this equation here, and I'm going to do that for the 1,3 process, so 1 to 3, and I'm going to subtract from it the 2,3 process, so that's this expression here. So just substituting in there and there for these two processes, and then expanding that out, and what I get is the delta U terms are here, and then the T delta S terms are here. So what happens is that because delta U is identical for both these states, these two terms are exactly the same, and they cancel out. So all that's left is that we have the minus the temperature times delta 1,3S minus, that's supposed to be delta 2,3S there, okay? And so now, doing a little rearranging of this becomes, the difference between the work becomes temperature of the surroundings times delta 1,2S. So you can see that I've taken this expression over here, and I've just expanded it out and recontracted it into this form here. So now it's the change in the entropy between state 1 and state 2, and that gives me this expression right here. So what we learn is that this difference in energy is got to be positive, because we know that from going from state 1 to state 2 that that's an increase in the entropy. So that's positive, temperature is positive, so the work difference has to be positive. If the work difference is positive, then remember, in both these cases, work is negative. It gets a little confusing with the signs. So that means that for this quantity to be positive, the magnitude of the 1,3 work has to be is greater than the magnitude of the 2,3 work. So be careful with the signs, but think through this very carefully. But what we learn from this is that for systems with exactly the same energy, more work is extracted from the ones with the lower entropy than the ones with the higher entropy. So having a lower entropy allows you to extract more work than you would from the higher entropy state. So from just the thermodynamics, that's one way we can think about interpreting the entropy as sort of the increase in the entropy is a loss of the ability to do work, of the system to do work. We've lost information in a sense that would have allowed us to extract work from the system. So let's continue on now to look at what happens during irreversible processes. So far, the definition we've looked at is only for the differential entropy for a differential heat flow under reversible conditions. But what happens if it's an irreversible process? So imagine we were comparing, like we've done before, an expansion process where we were doing a reversible expansion compared to some kind of irreversible expansion. If you remember, go back to the previous slide, you'll understand why this looks this way, because as we expand, the pressure behind the piston is much lower than the equilibrium pressure, so it follows a different path here. And so what we see in this case is that the change in energy of the system between 1 and 2 has to be the same, because those are the same two states, but the paths are different. So that means that the heat and the work will be different for these two paths, but in the end, the change in the energy, the internal energy, has to be the same, because state 1 and state 2 are the same, whether they're connected by the reversible or the irreversible path. So in terms of the first law, we would say that delta U is equal to the reversible heat flow plus the reversible work, but that also has to be equal to the the irreversible heat flow plus the irreversible work has to also be equal to the reversible heat flow plus the reversible work. So these have to be equal to each other, because delta U is the state function between 1 and 2. So that means that if we know up here that the irreversible work, the magnitude of the irreversible work is definitely less than the magnitude of the reversible work. So if the magnitude of the irreversible work is smaller than the reversible work, then in order to get the same delta U, that implies that the magnitude of the irreversible heat flow has to be smaller than the magnitude of the reversible heat flow. All right? So then if we take the signs into account, that means that Q reversible is going to be greater than Q irreversible. And if we divide both of those by the temperature at which this occurs, that gives us this expression where Q reversible divided by temperature is greater than Q irreversible. And this we recognize as the entropy defined for a reversible process. So now we see that substituting for this, the delta S, that tells us that for an irreversible process, delta S is always greater than the irreversible heat flow divided by the temperature. So for an irreversible process, we don't have an equality, we only have an inequality, but we have a limit here. So we know that the entropy has to be greater than whatever that irreversible heat flow is. All right. So that means then we will revise our expression for the differential change in the entropy for any process, reversible or irreversible, to be that it's greater than or equal to in the case of its reversible, the dq over t. So again, only for a reversible process do we have that. Okay, next video we're going to be looking at thermodynamic potentials.